Imagine a world where the air is as thick as water and the temperature is hot enough to melt lead. This isn't a sci-fi nightmare. It is the surface of Venus, where every piece of tech we've ever sent has been cooked alive in under 3 hours. For decades, the record for survival on this planet stood at just 127 minutes, held by the Soviet Venera 13 probe. Engineers solved the heat problem by packing the electronics in giant insulated titanium thermoses, but eventually the heat always wins. But what if we stopped trying to hide from the heat and started building electronics that actually enjoyed it? That is the radical shift happening right now at NASA's Glenn Research Center.
The problem isn't just that things get hot, it's that standard silicon, the stuff in your phone, literally stops being a semiconductor at these temperatures. At 460 degrees Celsius, the electrons inside silicon get so much thermal energy, they just start jumping everywhere. When electrons leak like this, the off state of a transistor becomes identical to the on state. Your processor essentially turns into a useless piece of conductive rock, losing all ability to process logic or data. To survive Venus, we don't need better insulation. We need a completely different material science. We need a substance that can hold on to its electrons, even when the environment is trying to shake them loose.
This is where silicon carbide, or SiC, comes in. It is a wide-bandgap semiconductor, meaning it requires significantly more energy to knock an electron into the conduction band compared to standard silicon. Think of it like a hurdle race. In normal silicon, the hurdles are low, and at high temperatures, the electrons can just step over them. In silicon carbide, the hurdles are 3 times higher, keeping the electrons exactly where they belong. This physical property allows SiC chips to function perfectly in temperatures that would turn a modern laptop into a paperweight. It is the key to creating a brain that doesn't need a refrigerator.
But the chip is only half the battle. On Venus, the atmosphere isn't just hot, it's heavy. The pressure is 90 times higher than Earth, roughly equivalent to being 3,000 feet underwater. Traditional electronic packaging uses hollow plastic or metal shells. On Venus, those shells would implode instantly. To solve this, NASA engineers turned to advanced ceramic structural architecture. By using solid ceramics and specialized interconnects made of gold and platinum, they've created a hardware stack with no air pockets. There is nothing to crush because the entire system is as solid as a brick.
The result of this engineering is a device that doesn't just survive for a few hours, it thrives for months. In recent tests, these circuits operated for over 60 days in simulated Venus conditions without any cooling at all. This isn't just a small improvement, it's a 1,000-fold increase in mission life. It changes the way we think about exploring the most hostile environments in our solar system. By mastering the physics of wide-bandgap materials, we've essentially built a new class of high-temperature hardened hardware that treats 460 degrees Celsius like a walk in the park. To understand why silicon carbide is so special, we have to look at the atomic level. In a standard silicon crystal, the bonds between atoms are relatively weak. Heat is just atomic vibration, and at high temps, silicon vibrates so hard its structure effectively softens for electrons. Silicon carbide is different. It's a compound of silicon and carbon atoms locked in an incredibly tight crystalline bond. It's actually one of the hardest materials known, nearly as hard as diamond. Because these bonds are so strong, they don't vibrate as much when heated. This stability is what allows the material to maintain its semiconductor properties while everything around it is glowing red hot. This atomic strength translates directly to the band gap, the energy gap between the valence band and the conduction band. In CIC, this gap is roughly 3.26 electron volts, compared to just 1.1 for silicon. This means that for an electron to leak and cause a short circuit, it needs a massive kick of energy. On Venus, the heat provides plenty of energy, but it's still not enough to jump the CIC gap. It's the ultimate electronic gatekeeper. By choosing a material with a wider gap, engineers have created a system that is physically incapable of failing the way standard electronics do. But a chip needs to talk to the rest of the probe. In standard electronics, we use solder to connect components. But on Venus, standard solder would melt into a puddle almost immediately. NASA's solution? They don't use solder at all. Instead, they use a process called thermosonic bonding with gold and platinum wires. These metals have melting points well over 1,000 degrees Celsius. The entire circuit board is a masterpiece of metallurgy. Every material was chosen because its thermal expansion coefficient matches the others, ensuring the board doesn't crack as it heats up from 20 degrees to 460. To protect these delicate connections from the corrosive Venusian air, which is filled with sulfuric acid, the entire assembly is encased in a specialized alumina ceramic package.
Alumina is incredibly dense and chemically inert. It acts as a physical shield against the pressure and a chemical shield against the acid, all while allowing heat to pass through so the chip can operate at ambient temperature. It's a complete reversal of traditional engineering. Instead of trying to keep the heat out, we've designed every single atom of the device to embrace it.
The complexity of these chips is currently low. We're talking hundreds of transistors, not billions like in your phone. But for a Venus lander, you don't need to run Crisis. You need to measure temperature, pressure, and wind speed. These simple chips are actually a massive leap forward. They represent the first time we've had a reliable, long-term electronic presence on the surface of another world without needing a massive power-hungry cooling system. And the clever part? Because they don't need cooling, the probes can be much smaller and cheaper, allowing NASA to send a whole fleet of mini landers instead of one giant expensive one. Before these chips ever reach Venus, they have to survive hell on Earth, the gear chamber at NASA Glenn. This is a massive steel vessel that can perfectly replicate the horrific conditions of the Venusian surface. Inside gear, engineers pump in a cocktail of carbon dioxide and sulfur dioxide, crank the pressure to 90 bar, and heat it to 460 degrees. It is the most accurate Venus simulating environment in the world. When the SiC chips came out of a 60-day run in this chamber still functioning perfectly, the engineering community was stunned. We had finally broken the 127-minute barrier.
This breakthrough is the heart of the LLISS mission, the long-lived in-situ Solar System Explorer. It's a small 10-centimeter cube designed to sit on Venus and broadcast weather data for months. LLISS is a masterpiece of minimalist engineering. It uses a high-temperature battery and SiC electronics to do what used to require a multi-ton lander. It is the ultimate lean spacecraft. By proving that we can operate logic gates in these conditions, we've opened the door to more complex machines, rovers that can actually drive across the Venusian plains without melting their brains.
But the implications of this tech go far beyond space exploration. The same silicon carbide engineering is already revolutionizing industries right here on Earth, from electric vehicles to jet engines. In EVs, SiC power electronics are much more efficient than silicon, allowing for faster charging and longer range. They can handle the high heat of fast charging without needing massive, heavy cooling systems. In jet engines, SiC sensors can be placed directly in the combustion chamber to monitor performance in real time. This allows for much more precise fuel control and lower emissions.
We are witnessing the birth of a new era in hardware, the unmeltable age. We're moving away from fragile electronics that need to be pampered and towards systems that are as rugged as the environments they inhabit. This transition is one of the most significant shifts in semiconductor history since the invention of the transistor itself. It's about more than just Venus. It's about making technology truly universal. When we design for the hardest place in the solar system, we end up creating tools that make everything on Earth better, more efficient, and more durable.
The next time you see a picture of the orange, hazy clouds of Venus, don't think of it as a graveyard for robots. Think of it as the ultimate proving ground for the future of human engineering. We finally learned how to build a brain that can stand the heat. And that means the secrets of our sister planet are finally within our reach, one silicon carbide atom at a time. From the crushing depths of a planetary atmosphere to the heart of a jet engine, unmeltable electronics are changing the way we see the world. And now you know exactly how they work.